Well, my friends, we will continue our journey through the valley of the shadow of confidence intervals. And in this particular video, we're going to examine effect size. Effect size is a very powerful way to help you visualize and construct a confidence interval. So we will get started here. Again, you may remember this awesome diagram. This is about the central limit theorem, which allows us to use x bar and s to take a sample, take its mean and its standard deviation to establish a confidence interval for mu with a given level of confidence. In other words, we can take a sample of size n, we can calculate x bar and s of the sample, and using x bar and s, we can construct a confidence interval for mu, which will, at a given level of confidence, which has a set z-score, which will give us a lower bounds for mu and an upper bounds for mu. This is extremely powerful. Now, given any confidence interval, the effect size is the distance above and below the mean required to capture the required percentage of data. For example, a 95% confidence interval has these boundaries, and it's this much above the mean and this many standard deviations below the mean, and the effect size for a 95% confidence interval is this distance right here, and the effect size is this distance right here. So you see that the confidence interval is described by mu plus the effect size and by mu minus the effect size. The plus the effect size gives us the upper bounds, minus the effect size gives us the lower bounds. Now, effect size is often denoted by E. E is the effect size. So here we have what I just said, that the confidence interval is equal to mu minus the effect size. Mu minus the effect size puts us right here, and mu plus the effect size puts us right here. Mu minus the effect size is the lower bounds, mu plus the effect size is the upper bounds. Now, a formula for defining the confidence interval for raw data values is really easy. The effect size is just the z-score times the number of standard deviations. So if you want an effect size, you want 95% confidence, your z-score is going to be 1.96 times your standard deviation, and that will give you your effect size. If your standard deviation is 3, it would be 1.96 times 3. Okay, now this is the z times the sigma of the population. The confidence interval for raw data for a sample is z times s. I actually believe that this is a much more important formula than this because we will know the standard deviation of the sample. Many times we will not know this, and most of the time we will not know the standard deviation of the population. Now, here's the important one. The confidence interval for an X bar distribution. You see, here's the effect size for a raw data distribution. The X bar distribution is how the X bars cluster around mu, and they're very tightly packed with mu, and their standard deviation is S divided by the square root of n. So the effect size here is equal to the z-score times the standard deviation of the X bar distribution, which is S over the square root of n. Notice that as n, the samples grow larger, that the effect size will become smaller because S divided by a larger and larger and larger number will give you a smaller value times Z, which will make a smaller effect size. This is the important formula. This one is theoretical, it's very good, it's wonderful to know, but since we will never probably know the mean of the population nor the standard deviation of the population, and probably not even the number in the population, we generally work with a sample where we know the standard deviation of the sample and we know the number in the sample, and of course we can calculate X bar for the sample. So a formula for the confidence interval for X bar, E will be equal to z-score, that's for your confidence level, 95%, 90%, 85%, 70%, 99%, whatever you want, that your confidence level determines the z-score, times S over the square root of n. And S divided by the square root of the n is the standard deviation of the X bar distribution. Now, if X bar is normally distributed around mu, then it follows that mu is distributed around X bar. Let's go back and think about that just a moment. Most of the time, we will never know mu. So if we don't know mu, it would be impossible to draw the distribution of all the x bars around mu. But if we do know x bar, and if we know x bar, then we can calculate around x bar a confidence interval using x bar plus e and x bar minus e, where e is equal to the z-score times s over the square root of n. We can calculate this confidence interval around x bar to have a given certainty that mu will be in this interval. I want you to think about that again. If x bar is distributed around mu, then mu is distributed around x bar. That's like saying if x bar stays with mu, then mu stays with x bar. I used to have a friend named Floyd. If Rusty and Floyd are together, then Floyd and Rusty are together. If you find Rusty, then you find Floyd, then you find Floyd, you find Rusty. That's a reciprocal. If x bar is around mu is descriptive, then mu is distributed around x bar is inferential. If we can calculate x bar, we can find s and we know n, then we can use the z-score to find an effect size to create a confidence interval for the true value of mu and do inferential statistics. For example, we're 95% confident that mu is in this interval and our z-score would be 1.96. This is the step that moves us from descriptive to inferential statistics. And now we can use a sample to predict the value of mu. In other words, we can take a sample, we calculate x bar and s, and then we calculate an effect size for the confidence interval for mu, using that the effect size is z times s over the square root of n, where z is the z value for your given level of confidence, s is the standard deviation of the sample, and n is the number in the sample. This gets to be a lot of fun. Again, I want to thank you very much for your support. Keep up the hard work. You've come far, and may the odds be ever in your favor.